Introduction to the rigid body rotations. Motion of a spinning heavy symmetric top. Introductory example. Central force motion. In this video, we will consider Kepler's laws and the central force motion. Kepler gave three laws concerning planetary rotations by studying mainly on the motion of the Mars. These three laws are: planets rotate around the Sun in elliptical orbits and the Sun is at one of the foci. The radius vector from the Sun to the planet swept equal areas in unit time. The square of the period of a planet is proportional to the cube of the semi-major axis. Kepler's laws explain the basics of the planetary rotations, but the solar system is a complex structure with many elements. You can see some of these in this picture: the Sun, planets, moons, and dwarf planets. All of them affect each other. In real cases, one may need to consider all of these together and include other effects, such as the local motion of the Sun and the motion with respect to the galactic center. Considering all of the planets, the Sun, and moons is hard enough to study with many human and technological resources on its own. Like Kepler, we will consider a more simpler case. We will consider two bodies having different masses, m1 and m2, and the distance between their center of masses will be taken as r, and we will consider that they attract each other. If they have enough initial angular velocities, then they rotate around their center of mass. And this line represents the rotation axis passing through the center of mass. This problem can be reduced to an equivalent one-body problem, in which a body with mass mu rotates in a central force field. To reduce to an equivalent one-body problem, we need this r, which will be taken as the same as this r, and it is equal to r2 minus r1. And we will consider this problem in this center of mass reference frame, in which we can write m1 times r1 plus m2 times r2 is equal to 0. And the total kinetic energy of these two bodies is equal to this one. And we need the equivalent of this kinetic energy in the equivalent one-body problem. One can write as 1 over 2 mu v square. Here mu is the mass of this body and v is the time derivative of r. And r1 and r2 can be written in terms of r by using this two formula, and one can find v1 and v2. Then one can find the relation between these two formulas, and by using that relation one can find the reduced mass mu as m1 times m2 over m1 plus m2. We will consider that these two bodies are interacting gravitationally, and the force between them can be written as minus gm1 times m2 over r square r hat. Then by considering F is equal to minus del U, one can write the potential energy as minus gm1 times m2 over r. For simplicity, we will take gm1 times m2 as k, and then one can write U is equal to minus k over r. Minus k over r potential energy gives a special case of the central force motion, which is a more comprehensive topic. In this video, we will only consider minus k over r case. It is possible to study the central force motion by using different methods. We will use Lagrangian formalism. Lagrangian is equal to T minus U, where T is the kinetic energy and U is the potential energy. And Lagrange equations are d over dt times del L over del Qi dot minus del L over del Qi is equal to 0, where Qi's are generalized coordinates and Qi dots are generalized velocities, and clearly this dot represents the time derivative. For rotational motion, if motion takes place in a plane, one can define the motion with two variables in polar coordinates, r and theta. In this case, r and theta are the generalized coordinates. It is possible to use different representations to describe the rotational motion. We will follow the convention and use two different representations. The first one is considering r and theta as functions of time, and the second one is considering r as a function of theta. We need to write the position vectorially, which requires unit vectors. It is possible to define r hat by considering the geometry of the system as cosine theta I hat plus sine theta j hat, and theta hat as minus sine theta I hat plus cosine theta j hat. Then we can write r vector as r of t times r hat, since r hat is always parallel to r vector. Now we will consider the velocity vector, which is equal to dr over dt. Before calculating this derivative, let us consider the change of r vector via this animated plot. This dotted line is a part of an ellipse, and this vector shows the position of an object following this elliptic orbit. As you can see, as time passes, the theta changes and the direction of this r vector changes, and also its magnitude changes. Let us see how these occurs in the calculations, and we have already written r vector as r times r hat, and here we have a derivative of a multiplication. Then we can write in this form. For the first term, we can write r dot times r hat, and for the second term, we need to calculate this derivative. Before calculating, let us remember the definition of r hat unit vector, which was given in this way, and we need to calculate the r hat over dt, which can be written as the r hat over d theta times d theta over dt by using chain rule. The second one can be written as theta dot, and we need to calculate the first one, and we need to take the derivative of r hat with respect to theta. From the first one, we obtain minus sine theta, and from the second one, we obtain cosine theta. And as you can see, it is equal to theta hat. Then we can write the r hat over dt is equal to theta dot times theta hat. By using this result, we can write the second term as r times theta dot times theta hat. Let us consider the components of the velocity vector. The first one is r dot times r hat, and for this case it is drawn in the reverse direction of the r vector. For this part of the elliptic motion, the magnitude of r decreases and r dot becomes negative, and this reverse direction shows the decrease of the magnitude of the r vector. And the second one is r times theta dot times theta hat. And as you can see, it is perpendicular to the r vector, and it is mainly related to the change of the direction of the r vector. We have obtained the velocity vector in this form, and by using t is equal to 1 over 2 mu v square, we can obtain the kinetic energy as 1 over 2 mu r dot square plus 1 over 2 mu r square theta dot square. And we have already mentioned that the potential energy is equal to minus k over r. Then we can write the Lagrangian by using this relation as 1 over 2 mu r dot square plus 1 over 2 mu r square theta dot square plus k over r. And we can write the energy by using this relation as 1 over 2 mu r dot square plus 1 over 2 mu r square theta dot square minus k over r. We have obtained necessary relations to study the motion in terms of generalized coordinates. Now we will obtain equations of motion by using Lagrangian. Lagrange equations for theta can be written in this way. And for the first term, we need to take the derivative of Lagrangian with respect to theta dot, and only relevant term is this one. And from the derivative of this one, we obtain mu r square theta dot. And for the second term, there is no theta dependence on the Lagrangian, and the derivative gives 0, and we obtain this equation. And we need to take the total time derivative. Only variables for this term are and theta dot. After taking this total time derivative and making some arrangements, one can obtain theta double dot as minus 2 r dot times theta dot over r. Let us do the same for r. The Lagrange equations for r can be written in this form, and for this one we need to take the derivative of this one and we obtain mu r dot, and for this one we need to consider these two terms, and the derivative of this term gives mu r theta dot square, and the derivative of this one gives minus k over r square. And we need to take this total time derivative, and only relevant term is this r dot. After taking this total time derivative and making some arrangements, one can obtain r double dot as r theta dot square minus k over mu r square. We have obtained two equations of motion. As you can see, theta double dot depends on r dot and r double dot depends on theta dot, which means that these two equations are coupled and they should be solved simultaneously, which can be done numerically. One can follow a different path, and one can consider this relation. This total time derivative is equal to 0, which means that mr square theta dot is constant, and we know that that constant is angular momentum. One can see this from the Noether's theorem. As you can see, the theta is not available in the Lagrangian, which means that Lagrangian is symmetric with respect to theta, or theta is cyclic coordinate. Then the corresponding quantity is conserved, which is angular momentum in this case. And by using this angular momentum, we can simplify theta dot in this equation, and we can obtain r double dot in this form. And this can also be solved numerically, and one can obtain r from this single differential equation. We have obtained one of the conserved quantities, angular momentum, and used it to simplify one of the differential equations. And there is another conserved quantity. In terms of Noether's theorem, there is time symmetry in the system, and the corresponding conserved quantity is energy, which we have already written in this form. And we can also simplify this one by using the angular momentum. And by simplifying theta dot, we can write the energy as 1 over 2 mu r dot square plus L square over 2 mu r square minus k over r. We have already obtained equations of motion and given them in two different forms and mentioned that they can be solved numerically. Now we will give another solution, which is an analytical one. We have already written energy in this form, and one can get r dot from this equation and write dr over dt is equal to square root of this function, whose only variable is r, the other ones are all constants. And from this result, one can write that dt is equal to dr over square root of this function, and one can integrate both sides and obtain this result. This integral can be found in an analytical way. However, it is a bit messy and it is a conditional integral. Then we will not write it explicitly, but in principle, after writing the result of this integral, one can obtain r in terms of t, and by using that result one can obtain theta dot and correspondingly theta. There is another solution, and it is better in some ways, and this method also uses conserved angular momentum and energy. We have already written theta dot and r dot in these forms by using these two relations, and d theta can be written as d theta over dt times dt over dr times dr. The first term is theta dot and the second term is 1 over r dot. Then d theta can be obtained as theta dot over r dot times dr. Since this part will be integrated over r, we will write theta dot and r dot in terms of r by using these two relations, and d theta can be obtained in this way. After some simplifications related to mu's, d theta can be obtained in this form. We will carry out this integral by changing variable, and we will say u is equal to L over r, and du is equal to minus L over r square. then d theta can be obtained in this form, and we will carry out this integral by using this result, which can be found in integral tables, and c is the integration constant. Then theta can be obtained in this way, and we will change the variable back and we will make some arrangements. Then one can obtain sine theta minus c is equal to 1 minus L square over mu kr over square root 1 plus 2el square over mu k square. We have obtained solution and we will make some arrangements. Firstly, we will define L square over mu k as p and square root 1 plus 2el square over mu k square as e. Choosing these letters will be clear later. Then we can write sine theta minus c is equal to 1 minus p over r over e. Then we can write r in terms of theta in this way, p over 1 minus e sine theta minus c. And we can make some further arrangements, and we can write sine theta minus c as cosine by subtracting pi over 2 from the argument of sine. And by considering that the minimum of r occurs at theta is equal to pi, we can write sine theta minus c as cosine theta. Then we can write the solution as r is equal to p over 1 minus e cos theta. We have obtained r in terms of theta, and this solution gives all conic sections, which we will consider later. And let us consider p and e. P is the semi-latus rectum. Latus rectum is this chord passing through one of the focal points and parallel to the directrixes. And semi-latus rectum is half of this one, and E is the eccentricity. And there are different representations of this solution, and one can find them on the web page of the University of Texas at Austin. It's possible to check this solution satisfies the equation of motion for r by using the chain rule in this form of the equation of motion, or one can use this form of the equation of motion, which can be obtained by using the chain rule. We have obtained the solution, and an educated person can see from this solution all possible situations. However, it is not easy to gain such a background, and we will explain all possible cases. Before explaining possible cases, we will approach the problem from a different perspective. We will consider an effective potential to understand different orbits. As it can be seen from this form of energy, it is function of r dot and r only. So we can consider this motion as one-dimensional motion, though in reality it is a two-dimensional motion. The first term of this expression can be considered as kinetic energy, and the remaining two terms can be considered as potential, or with the correct terminology, as effective potential for considered one-dimensional motion. And we will use this effective potential to understand the motion. Let us try to understand the structure of this effective potential, and we will firstly consider the second term minus k over r, which is shown by this dashed curve. And as you can see, as r goes to infinity, it goes to 0 from below. And as r goes to 0, it goes to minus infinity. And one can conclude from this that if there isn't any rotational motion or angular momentum, which makes the first term 0, then gravitationally attracted two bodies will collide, since there isn't any turning point on the left side. If there is a rotation, the term L square over 2 mu r square contributes to the effective potential, and its structure is shown by this dashed curve. As you can see, as r goes to infinity, it goes to 0 from above, and it goes to 0 faster than minus k over r term. And as r goes to 0, it goes to infinity, and it goes to infinity faster than minus k over r term. This blue curve shows the effective potential, which is total of these two terms. And as you can see, it goes to 0 from below, since L square over 2 mu r square goes to 0 faster than minus k over r term, and it goes to infinity since this term goes to infinity faster than minus k over r as r goes to 0. And as you can see, effective potential becomes 0 at this point. At that point, R is equal to L square over 2 mu K, and there is a minimum of this effective potential. Let us say that this minimum occurs at Rm, and we can find that Rm by taking the derivative of the effective potential with respect to R, and which is equal to minus L square over mu R cube plus K over R square. Then Rm can be found as L square over mu K, and it is equal to semi-latus rectum. And if we put this value to the effective potential, we can obtain the minimum of the effective potential as minus K square mu over 2L square. As you can see, Rm and the minimum of the effective potential depends on L square and parameters of the motion, and does not depend on variables R and R dot. And different orbits can be inferred from the graph of the effective potential and energy. Energy can have different values. It can be equal to the minimum of the effective potential. It can be between 0 and the minimum of the effective potential. It can be equal to 0, and it can be greater than 0. Each of these cases corresponds to different conic sections. Now we will study these possibilities. Before studying different possibilities, we should note that if E is smaller than the minimum of the effective potential, then there is no orbital motion, and the two gravitationally interacting bodies will collide. The first conic section that we will consider is the circle. This type of orbit is seen when energy is equal to the minimum of the effective potential. In this case, energy is negative. This may seem strange, but for bound cases, it is natural to have negative energy. For this case, there's only one possible R value, and it doesn't change throughout the motion, which gives a circle, as we already mentioned. The equation for the circle can be written as x square plus y square is equal to R square. And dividing both sides with R square, we can write it as x square over R square plus y square over R square is equal to 1. For the circle, eccentricity is equal to 0, then R becomes equal to P, which is equal to L square over K mu that we have already seen. And for this graph, the violet curve is drawn by considering these values and calculating R value. And black dots show the results of the numerical solution of these two coupled differential equations. Here we see an animated plot of the numerical solution. As it is seen, the rotation direction is chosen as the counterclockwise direction, and this orbit is circular. In these animated plots, we see the orbit again at the left and the effective potential at the right. This black dot shows the position of the R value. And as it is seen, as our objects follow the circular orbit, the R value does not change as expected. And in these graphs, we see the effective potential at the left and the components of the velocity at the right. As it can be seen, R dot is equal to 0 and R theta dot is constant. And these results show that angular momentum, which is equal to mu R square theta dot, is constant. The second conic section that we will study is the ellipse, which is observed in the central force motion when the energy is between 0 and the minimum of the effective potential. As it can be seen, E intersects effective potential at two different points. This means that there are two distinct turning points, and R takes values between these two values. As E approaches to 0, bigger ellipses are observed, eccentricity approaches to 1, and the period of the orbit increases. As E approaches to the minimum of the effective potential, smaller ellipses are observed, eccentricity approaches to 0, and the period of the orbit decreases. Here we see an ellipse. The origin of the coordinate system is set to the center, and the equation for this ellipse can be written as x square over a square plus y square over b square is equal to 1. Due to its relation with Kepler's laws, we will consider the ellipse in more detail to remember some of its properties. If we move the center of the coordinate system to the focal point of the ellipse, The ellipse equation can be written as x minus c square over a square plus y square over b square is equal to 1. And this horizontal chord is equal to 2a and the vertical chord is equal to 2b. Both of them passes through the center of the ellipse. And there are two focal points for the ellipse and the distance between them is equal to 2c. And the eccentricity of the ellipse is equal to c over a, and it is always between 0 and 1. There is a useful property of the ellipse. If we choose a point on the ellipse such as a, then the total of the distances from that point to the focal points is equal to 2a. We will use this property. If we choose the upper point of the minor axis, we obtain this configuration, and this is a right triangle. Then b square plus c square is equal to a square. And by using eccentricity is equal to c over a, b can be obtained as a times square root 1 minus e square. And the area of the ellipse is equal to pi times AB. To understand the relationship between the ellipse and the central force motion, we should obtain the relation between the parameters of the ellipse and the central force motion. To do this, let us consider elliptic orbit and intersections of the ellipse with the major axis and show these positions as R1 and R2. R1 is the farthest point and can be considered as apollyon for the rotation around the Sun, and R2 is the closest point and can be considered as the perihelion for the same motion. Let us consider the change of R on the elliptic orbit. After the position of R1, it decreases till R2 and then it increases till R1, and at the positions R1 and R2, it doesn't change momentarily. Let us calculate R1 and R2 in terms of the parameters of the central force motion. We have already written energy in this form, and we have seen that at R1 and R2, R does not change, which means that R dot is equal to 0, and energy can be written in this form. Then we can rearrange this equation in this way. This is a quadratic equation in R, and its solution can be written in this way. We can use these solutions to obtain the relation between the central force motion and the elliptic orbit, and this relation can also be used for other conic sections. We have already said that horizontal chord is equal to 2a. In this case, it is the major axis, and as it can be seen from the figure, the addition of the magnitudes of R1 and R2 is equal to 2a. Then the second terms in this addition cancels each other, and we get the results a is equal to minus k over 2e. And remember that for elliptic orbits, e is smaller than 0. As it can be seen, 2c is equal to the difference between the magnitudes of R1 and R2. In this case, the first term cancels each other, and one can obtain c as 1 over 2 square root k square over e square plus 2l square over mu e. Then we have obtained a and c, and by using this right triangle and the relation a square is equal to b square plus c square, b can be found as L over square root 2 mu absolute value of E. Now let us return to the central force problem and consider the situation in polar coordinates. We have already obtained the solution, and we know P and E in terms of the parameters and conserved quantities of the central force motion, and the eccentricity is always between 0 and 1. The violet curve is drawn by using this relation for these parameters, and black dot shows the results of the numerical solution of these coupled equations. This is the animated plot of the numerical solutions, and as it can be seen, it starts from the minimum R value and it completes the ellipse. And in this animated plot, we see the elliptic orbit at the left and the effective potential and energy at the right. This black dot shows the R value corresponding to the orbital motion. And as it can be seen, R changes between the intersection points of the energy and the effective potential, which are the turning points. Here we see another animated plot. Again at the left we see the orbital motion, and at right we see angular momentum r and r theta dot. As it can be seen, angular momentum is constant, and angular momentum can be written as mu times r theta dot. And as it can be seen, r increases in the first half and r theta dot decreases in the first half, and in the second half the changes takes place in the reverse order. Here r theta dot is the tangential component of the velocity vector, and as it can be seen, its changes takes place in order to obey the conservation of the angular momentum. We will consider one more thing for elliptic orbits, the changes in velocity components in polar coordinates. We have already seen that the changes in r theta dot, the tangential components, obey the conservation of angular momentum, and the changes in r dot can be understood from the effective potential, since the difference between the energy and the effective potential is 1 over 2 mu r dot square, and this is proportional to the square of r dot. And the changes in effective potential between turning points is very similar to the r dot, and in the second half of the motion the changes takes place in the reverse order. The third conic section that we will consider is the parabola, which is observed when e is equal to 0. For the most known parabola y is equal to x squared, the parabola opens upward and y is the principal axis and the bottom point of the parabola is at the origin. But we will consider a different parabola to get a coherent graph with the polar form of the previously obtained solution. For this parabola, x is equal to y square over 2p minus p over 2, and the x-axis is the principal axis and the origin sits at the focal point and the parabola opens rightward. This parabola can also be obtained from the polar form of the solution, and for the parabola e is equal to 0, then eccentricity becomes equal to 1, and the p, the semilatus rectum, can be seen here, and it can be obtained when theta is equal to pi over 2, and this r1 can be obtained when theta is equal to pi as p over 2. Similar to the previous cases, this violet parabola is drawn by considering the polar form of the solution for these parameters, and the black dot shows the results of the numerical solution of these coupled equations. This is the animated plot of the motion, and we see that as r gets smaller, the motion becomes faster. This animated plot shows the orbit and the effective potential. Again, black dot shows the position of the r corresponding to the motion, and we see that r gets smaller values till the intersection points and gets bigger values after that one, and since there isn't any upper turning point for this motion, it does not return. In this case, the trajectory does not repeat itself, which is different from the circular and elliptic orbits. Now we will consider L, R, and R theta dot. As it can be seen, L does not change throughout the motion, and in the first half of the motion R decreases and R theta dot increases, and in the second half the changes occurs in the reverse order, and the changes in R theta dot obeys the conservation of angular momentum. Here we see the effective potential and the components of the velocity in polar coordinates, and the form of the r dot again can be inferred from the effective potential graph. Now we will consider the fourth and the last conic section, hyperbola, which is observed for the central force motion when E is positive. As E approaches to 0, the hyperbola becomes more similar to the parabola and the eccentricity approaches to 1 from above. And as E increases, the arms of the hyperbola becomes wider and the eccentricity gets higher values than 1. And as E goes to infinity, the hyperbola approaches to a vertical line and the eccentricity approaches to infinity. In this figure, we see a hyperbola whose equation can be written as x square over a square minus y square over b square is equal to 1. If we shift the origin to the focal point, then we can write the equation as x plus c square over a square minus y square over b square is equal to 1. In this figure, we see the parameters of the hyperbola. In this case, this horizontal line represents the principal axis. M is the center and C is the distance from center to the focal point over the principal axis, and A is the distance from center to the hyperbola over the principal axis. B is the vertical distance from the intersection point of the hyperbola and the principal axis to the asymptote. These are the asymptotes, and they are the lines drawn from the center M to the asymptotic value of the hyperbola at the infinity, and the hyperbola approaches to these asymptotes as x or y goes to infinity. And P is the vertical distance from the focal point to the hyperbola. By using a similar technique used in the calculations of the elliptic orbit, one can calculate A and C in this way, and one can also calculate the B by using this right triangle and this relation. And the eccentricity can be calculated by using C over A in this form, and it is always greater than 1 for the hyperbola. We can draw a hyperbola by using the polar form of the solution. We see an animated plot showing how hyperbolic curves correspond to the angle of the polar coordinates when it is between 0 and 2 pi. As it can be seen, the left down quarter is obtained from smaller values of theta, the right branch is obtained from the middle values of theta, and the left upper quarter of the hyperbola is obtained from the greater values of theta. The exact angles can be determined by using the value of eccentricity. These two branches of the hyperbola are drawn by using this polar form of the solution for these values. And again, the black dots are obtained from the numerical solution. As it is seen, only one of the branches is obtained from the numerical solution. This is the animated plot of the numerical solution. As it can be seen, as r gets smaller values, the velocity increases. This is animated plot together with the effective potential. Again, black dot shows the position r corresponding to the orbital motion, and this point is the intersection of the E with the effective potential. Similar to the parabolic motion, r gets smaller values till the intersection point and then gets bigger values. This motion does not repeat itself since there isn't any turning point for the right side. Now we see L, R theta dot together with the motion. Again, L does not change as expected. The change in tangential velocity obeys again the conservation of angular momentum. These graphs show the effective potential and the components of the velocity in polar coordinates. Again, the form of the r dot is similar to the form of the difference between the energy and the effective potential. We have studied four conic sections which can be seen in the central force motion when the potential energy is equal to minus k over r. At the beginning, we explained that there are different solution methods, and one of them is finding numerical solution from these coupled differential equations, which we have already used in all cases. Another solution method is eliminating theta dot in the differential equation for r in the first solution method, and one can obtain a single differential equation by this method, and at least one can solve this differential equation numerically and obtain r, and then by using that result one can find theta dot, and by integrating theta dot one can find theta. We have also mentioned that by finding time from this integration and inverting the result, one can find r as a function of time, and then similar to the previous method, one can find theta by integrating theta dot over time. However, there is a drawback to this method. One can carry out this integral at most for half of the period. The last method is obtaining polar form of the solution by finding theta from angular momentum by using energy. However, there is also a drawback to this method. The time dependence of r and theta is lost. We have already used first and fourth method while studying different conic sections. Now we will show that the first three methods give consistent results. Here we see the results for mentioned three methods. Since for the third method it is only possible to carry out integration for the half of the period, we will compare results for the change of r for the half of the orbit. Blue curve shows the results of the first method and red dot shows that of the second one, and the triangles show that of the third. Here the triangles are not evenly spaced since the integration is carried out with respect to r. As it is clearly seen, all three results are consistent, and from the studied conic sections we know that first and fourth method are consistent, which means that all four methods are consistent. For the shown case, the initial values or parameters are the same as the previously considered elliptic case. Now let us revisit and consider Kepler's laws. We have already seen that elliptic orbits are possible for central force motion, which is consistent with Kepler's first law. However, we have seen that other conic sections are also possible, and we know that some objects follow hyperbolic orbits in the solar system. Circular and parabolic orbits require fine-tuned parameters, which may not be possible for the solar system, since there are always other effects. Kepler studied only observations related to the planets, and all of the planets follow elliptic orbits with some small deviations due to other factors, like effects of other planets. Now let us study the second law of Kepler. The radius vector from the Sun to the planets swept equal areas in unit time, or in short, dA over dt is constant. In this figure, we see an area of the elliptic section when the radius vector swept an angle delta theta. If we consider the limit that delta theta goes to d theta, then dA can be written as 1 over 2 r square d theta, which can be obtained by integrating dA is equal to r dr d theta over r. And we need to show that dA over dt is constant according to Kepler's second law. Then we can write dA over dt from this one as 1 over 2 r square d theta over dt. This is theta dot, and we know that it is equal to L over mu r square. Then we can write dA over dt as 1 over 2 r square L over mu r square. R squares cancel each other and remains L over 2 mu. We know that L is constant since the angular momentum is conserved, and mu is also constant. Then dA over dt is equal to a constant. This shows that for elliptic orbits, Kepler's second law holds. Let us try to understand this law. While studying elliptic orbit, we have seen that as r becomes smaller, the tangential velocity increases. And according to these calculations, the amount of the change in the tangential velocity is exactly equal to the necessary one to keep the area swept by the radius vector from the center to the orbit constant in unit time. This means that if you consider some amount of time and calculate the area swept by the radius vector for some part of the motion and do the same for some other part of the motion, you will get the same value. While doing science, we use conserved quantities or constants of motion. Just like this case, if we are able to find a conserved quantity or constant of motion, then we can carry out our calculations more easily, and more importantly, we understand the situation better. Now we will consider Kepler's third law. The square of the period of a planet is proportional to the cube of the semi-major axis, or in short, t square is proportional to a cube. The area of the ellipse can be written as pi times AB, and we can write this one as pi times h square times square root 1 minus e square. And we have already obtained that dA over dt is equal to L over 2 mu. And we can integrate this one over time for the whole period and obtain A is equal to L over 2 mu times t. These give the necessary relation between period t and the parameters of the ellipse, and we can write that relation in this form. Now we need to write angular momentum in terms of the parameters of the ellipse. which we have already obtained the necessary relation while studying the elliptic orbits, as A is equal to minus k over 2e and B is equal to L over square root 2 mu absolute value of E. And we can simplify L by using this relation and obtain this one, and we can simplify E by using this relation and obtain this one. And we can simplify A times square root 1 minus E square from both sides, and we obtain this relation. And after taking the square of this one, we obtain this one, and after some arrangements, we obtain T square is equal to 4 pi square mu over K times A cube. Then the Kepler's third law is also obtained for elliptic orbits when the central force motion with minus k over r potential energy is considered, which corresponds to the gravitational interaction. This law opens the way for finding the period of a planet after calculating its semi-major axis or vice versa. This may seem unimportant. Let us consider the historical developments and then conclude. Since the ancient times, humanity were familiar with 5 classical planets. These are Mercury, Venus, Mars, Jupiter, and Saturn. Through the thousands-year observations, we were knowing their approximate period. After the scientific works of Copernicus, Galileo, Kepler, and other scientists, the situation is changed and the Earth is also considered as a planet. Uranus is discovered by William Herschel at 13 March 1781, and Neptune is discovered by Johann Gale, Urbain Le Verrier, and John Adams at 23 September 1846. If the Kepler's third law is not available to the scientists, we will need to wait for 84 years for Uranus to know its period, and 165 years for that of Neptune, which means that we could only able to know the period of Neptune in 2011. If we consider the dwarf planet Pluto, which is discovered by Clyde Tombaugh at 18 February 1930, we need to wait for 248 years till 2178, and we were not able to know its period today. We would need to wait for nearly 1.5 centuries more, which means that most probably none of us living today would not be able to know it. This is a simple approach. These laws help to understand the celestial objects also in other ways. We have studied central force motion and Kepler's laws, which are the basics of planetary rotations. There are much more physics and interesting things in the solar system. To learn these, one needs to attend related courses or study relevant materials. You can find references here. Thank you for watching.